And that is why now people like myself have raised the question, is ADHD executive function deficit disorder? Have we simply given it the wrong name, a very superficial name that doesn't really represent this wide swath of mental faculties that are being disrupted in this disorder? And that's what we're going to answer in this lecture. Is ADHD EFDD? And the answer, of course, is yes. It has to be, given the description of the individual's behavior and symptoms I just went over. ADHD really is EFDD under the wrong name. But beyond these behaviors that show these executive functions are involved, the neuroanatomy of ADHD and what causes it also points directly at the brain's executive system. And the neuropsychology of ADHD, as we understand it, includes all of these executive functions. So all of this virtually guarantees that ADHD really is executive function deficit disorder. And since I'm going to show you that the executive functions are what give us the ability to regulate our own behavior, to show self-control, then it means that ADHD isn't just EFDD, it's also self-regulation deficit disorder, or SRDD. They're all the same. So let's take a look at how we get from the clinical view of ADHD as everybody else sees it to the executive functioning view of ADHD as I and many other scientists have come to see this condition. So let's take a quick look at the neuroanatomy of ADHD, which clearly implicates the parts of the brain involved in executive functioning. We know that there are 7 major brain networks involved in brain functioning. And we know that at least one of them is the brain's executive system. And while we can split these 7 major networks into 17 minor ones, that doesn't concern us in this lecture. What we want to know is that one of the 7 major networks is the executive functioning network that gives us self-regulation. And although all of these networks involve the gray matter cortex of the brain and the basal ganglia deep inside the brain, as well as the thalamus, which is adjacent to the basal ganglia, and then the little brain at the back part of our head, which is the cerebellum. All of these are involved in these various brain networks. They are really essential for the executive network. And we know that ADHD involves at least a 3 to 10% reduction in the size of these areas of the brain, and that they involve at least a 10 to 25% reduction in how active these brain areas are. Even more important is how variable, how erratic these brain functions are, so that when they're functioning, they're not functioning as well, and they're quite variable in how well they function over time. So variability is as important to understanding the brain functioning of ADHD as is the smaller brain size in these brain regions. And of course, we now have evidence to show that these various brain structures are about 2 to 3 years delayed in their neurological development. And of course, the brain structures I'm talking about are the frontal cortex here at the front part of the brain, particularly known as the orbital frontal cortex, right at the very front pole of the brain. And then these parts of the brain send nerve cells down deep into the brain to a structure called the basal ganglia. And that is smaller and less active and not functioning very well. And then there are fibers or networks that go from there to the back part of the brain where the cerebellum is located. And that links up the cerebellum with the executive network. And then at the very front part of the brain, right between the two brain hemispheres, in that little valley or fissure. If we look on the walls of the inside surface in that valley, we will see the anterior cingulate, very important for executive functioning, as we will see. And this too is smaller and less active and not developing on time. And then to some extent, these various networks go through the anterior cingulate and project onto a structure called the amygdala. The amygdala is part of the brain's limbic system. The limbic system is the emotional brain. And as we will see, it is through this circuit that emotion regulation is possible. That is, the control of our emotions in a mature way to help support our goals. Some people think that the hippocampus and thalamus are involved in this, but that's not so clear. Now, these neuroimaging results show us that the size of these areas is smaller, and we know that the size of these regions is directly correlated with how severe the ADHD symptoms are going to be. So there's no question that we know where in the brain ADHD is coming from, and we know that it is due to an immaturity and poor and variable functioning in these parts of the brain. For the most part, there are very few, if any, important differences between boys and girls in these parts of the brain and their development. There are a few, but they're not worth talking about today. And we know that these differences in brain volume, that is the size of the brain, even though it's delayed and smaller, by late adolescence, it does catch up and it does begin to resemble the size of more typical brains. So while the size of the brain might normalize with age, the functioning of the brain and of the executive circuitry often does not. There remain problems with how the circuits connect, function, and how variable they function over time. We know that these differences in brain functioning and brain size have nothing to do with giving children stimulant medication. Some critics of ADHD have argued that it's the medication we use to treat the disorder that is causing these differences in the brain, and that's simply not true. We find these results even when we study children and adults who have never taken ADHD medications. So it certainly can't be that. It's part of what ADHD really is. The genetics of ADHD are what are leading to these problems in brain growth, wiring, and functioning. And there is some evidence that we have now accumulated in more than 30 studies that if you stay on your ADHD medications for several years or longer, particularly the stimulant medications, then there might just be promotion of brain development in these areas that are smaller and less developed. That is to say that children who have stayed on medication for several years or more actually show some normalization of their brain development from using these medications. Now, I want to be clear. This doesn't happen for everybody. Only about 25 to 40% of people taking medication show this renewed brain growth and possible normalization. We don't know a lot about this. We don't know which drugs do this and at what doses and how long you have to stay on them. But we do have a growing body of evidence that suggests that the medications in some people might well promote brain growth and development and possibly normalization. Now, here's a figure from a very important study published more than a decade ago that was done here in the United States and Canada by Dr. Shaw and many colleagues. And it followed over 220 ADHD children and normal or typical children. It followed them for over 10 years. And it took measurements of brain functioning using neuroimaging known as functional neuroimaging and structural neuroimaging. And it imaged the brains of these children every several years for up to 10 years. And when you do that, you can calculate how delayed the brain might be in people with ADHD. And this is the image that comes from looking across brain development. What you see here is that the darker the colors, the more delayed the brain development is. In this particular image, it has to do with the outside surface of the brain, known as the gray matter or cortex of the brain. And it's very remarkable that a large part of the brain in children with ADHD is quite delayed in its maturation. And much of that, as you can see here, has to do with the front part of the brain, known as I've said, the prefrontal cortex or the frontal lobes. And you can see it here as we look at the right hemisphere of the brain, and here as we look at the left hemisphere, that both hemispheres are quite delayed in their development. And it looks as if the right side might be a little more delayed than the left, but that's not so important to my lecture today. So here is one of the first studies to give us unequivocal evidence that the brain is not developing well in people with ADHD, and that it's about 2 to 3 years behind. That's very important. Now, I just want to spend a moment and call your attention to the back part of the brain that you see here, or if we look from the top down on the brain, we can see it here at the back part. As we know from our studies of the brain, this is involved in vision and in visual imagery. So this is the association center of the visual cortex. And you might wonder, well, what does that have to do with ADHD? I understand the frontal lobes. That's where the executive functioning is going on. But why would the back part of the brain, particularly down here, where vision is located, be involved in this? And as we'll see shortly, one of the executive functions, as I said, is working memory. And working memory can be split into two kinds: verbal or language, verbal working memory, which involves talking to ourselves, and visual working memory, which involves holding images in mind. And that's why this part of the brain is involved in ADHD, because it tells us that visual working memory, or the visual imagery system, is very much impaired in ADHD in addition to the rest of the frontal circuits. Now here's a diagram that shows the neuropsychology of the frontal lobe, and we can see that it implicates 4 different executive circuits or networks. And let's talk about those networks, and you can see that each of them goes to a different part of the brain. So we have the inhibition system, and we have the self-monitoring system, and we have the working memory system that guides behavior and so on. And then we have the emotion regulation system here that goes back to the amygdala that I mentioned to you earlier, and from there to the rest of the limbic system. So here are the circuits we're going to talk about very quickly to show you what is going wrong in the neuropsychology of ADHD and why many of us believe that this supports viewing ADHD as a disorder of executive functioning. The first circuit goes from the frontal lobe into the basal ganglia, and it's called the frontal striatal thalamic circuit. You don't need to worry about these terms, but let's look at what it does. This is the circuit where what we think about, what we hold in mind, is going to guide our actions and behavior. So what I think controls what I do. What I hold in working memory, my goals and plans, can actually be used to control my behavior and guide it over time. People think of this as the working memory circuit. I think of it as the what circuit. What I'm thinking guides what I'm doing. That's very important. The second circuit goes from the frontal lobe back through the middle part of the brain to the cerebellum. Well, what does that circuit do? That's the when circuit, the timing circuit. It's responsible for executing behavior, for carrying out our actions when it is most ideal and timely to do so. So we're thinking of it as the timing circuit of the brain. And as we all know, when we choose to pursue a goal can be very important to its success. It's not just about what we're going to do, but when we're going to do it. And that's the timing circuit. And it tells us that people with ADHD have massive problems with timing, with time management, with their sense of time, and using that sense of time to execute their actions and their plans so that they can optimize their results. And they don't do that very well. They have a very poor sense of time, and their time management is terrible. The third circuit goes from the frontal lobes, again, the executive brain, through the midline of the brain of the frontal lobe, that anterior cingulate I mentioned earlier, into the amygdala and the limbic system. As I said, that's the emotional brain. So here is where what I think controls how I feel. And of course, it goes the other way too. How I feel is going to influence what I'm thinking about. So it's kind of reciprocal, bidirectional. Thinking controls emotions, and emotions have some influence on what we're thinking about. So this is very important because this is where the top-down control of emotion takes place, the self-regulation of emotion, to make it so that it's consistent with our goals and our plans, and in general, consistent with our long-term welfare. The final circuit goes from the frontal lobes into that midline, and then to the back part of the brain, especially on the right side here, known as the posterior hemisphere or parietal lobe. And this is the circuit for self-awareness. This is where we are monitoring what is going on in space around us, but also monitoring what we're doing in that space at that time. Self-awareness. So we can see that the executive circuit involves 4 sub-circuits. One involves working memory, holding in mind what we're doing and doing it. The second involves timing, making sure that we're doing what we're supposed to be doing when it's important to do it. There's a deadline. There's a certain amount of time we have to get this done. Can we do that in time, on time, over time? And that's the second circuit. The third circuit is the hot circuit, the emotional circuit. This is where we control our emotions to be consistent with our plans and our goals. Emotional maturity, self-regulation of our feelings and our motivations. And then the last one is the self-monitoring circuit, the self-awareness circuit. Now, you can see then why ADHD disrupts all of these executive functions, because ADHD is a disturbance in the development of the brain's executive circuits and networks. And that leads to what we see in daily life in the deficits that people with ADHD have. So I hope I've shown you